Okay guys, let's begin the discussion over the questions. First question is to differentiate this given function with respect to x. The function you can just take as f of x. It's given to be e to the power 3 log x. You know by the property of log, I can write this as log of x cube. Exponential of logarithmic of x cube itself gives you x cube, because exponential and logarithmic to the base e, they are actually inverses of each other. And so e to the power log x cube is x cube, and therefore if it is asking us to differentiate f of x with respect to x, that means I am only supposed to differentiate x cube, because f of x is coming out to be equal to x cube on simplification. You know that d by dx of x to the power n is n into x to the power n minus 1. So d by dx of x cube is 3 into x to the power 3 minus 1, which is 3x square, and therefore f dash x, that is differentiation of fx with respect to x, where fx is e to the power 3 log x, is 3x square. Next question says what? It says that if limit of this function is 9, find the value of a. Here if you write this particular expression, limit x tends to minus a, x to the power 9 plus a to the power 9 upon x plus a equals 9. You need to find out the value of the unknown a. The moment I look at this expression, there is one particular type of limit which I am able to recall, which was limit x tends to a, x to the power n minus a to the power n upon x minus a is equal to n a to the power n minus 1. Remember? Right now n is being played by 9. Here what was happening is minus sign was there, and a that you can see was the point to which x was tending. Over here x is tending to minus a, but minus a is not sitting over here, but I can manipulate this given expression into what? Limit x tends to minus a, x to the power 9 minus minus a to the power 9. Can I write it like this? Minus a to the power 9 is minus of a to the power 9, minus minus will give me plus, I will be back with the same numerator, whole upon x minus of minus a, which eventually gives you x plus a. This is equal to 9. I have just rewritten the same thing in order to match it with this expression. If I take minus a equals b, in this situation we have limit x tends to minus a becomes limit x tends to b, x to the power 9 minus minus a to the power 9 means b to the power 9, whole upon x minus minus a means x minus b. This is given to be 9. Just in place of a, if you replace b, you have this very same left hand side, limit x tends to b, x to the power n minus b to the power n upon x minus b is n b to the power n minus 1, where n is being played by 9. So this will be n b to the power n minus 1, that is 9 minus 1. So this is 9 minus a to the power 8, because b is minus a, 9 minus 1 is 8, this is 9, 9 cancels out, you have minus a to the power 8 is actually a to the power 8 is 1, that means a is plus minus 1, right? Because minus 1 to the power 8 is also 1 and 1 to the power 8 is also 1. These are the only two real values whose power 8 gives you 1. Clear? Next question. If fx is x to the power n and f dash 1 is given to be 10, find the value of n. Okay, so in here fx is given to be x to the power n and f dash's value at 1 is given. In general, if fx is given to me as x to the power n, then f dash x for any x comes out to be n x to the power n minus 1. In particular, f dash 1 will be n into 1 to the power n minus 1, 1 to the power n minus 1 is 1, and f dash 1 is given to me as 10, and therefore directly I have got the value of n as 10. Understood? Moving to the next question, we have differentiate this function with respect to x, and the function is x sin x log x. If you take fx as x sin x log x, I am interested in f dash x, that means d by dx of fx. Now in here you can carefully see I am interested in considering x as one function and sin x into log x as another function. Clear? If you take this as one function and sin x into log x as another function, here product rule will be applied. Apply the product rule, what do you get? D by dx of 1 into 2 is 1 into d by dx of 2 plus 2 into d by dx of 1. So 1 into d by dx of 2 plus 2 into d by dx of 1. This is x. Now again you have d by dx of sin x into log x. Sin x I will be taking as first function, log x I will be taking as second function. Again product rule, d by dx of sin x into log x is d by dx of sin x into log x is sin x, that is 1 into d by dx of log x plus second into d by dx of sin x plus sin x log x d by dx of x is 1, so into 1 leaves it the same expression. This is x sin x into d by dx of log x is 1 by x plus log x d by dx of sin x is cos x plus sin x log x. Just open the bracket up, everything we have resolved. This is x sin x into 1 by x, x cancels out, you are just left with sin x plus x into log x cos x plus x log x cos x plus sin x log x, and that happens to be my very d by dx of fx, which we say f dash x. We have differentiated this given function using product rule twice. Next question we have, evaluate this given limit. Let's try to evaluate the value of this limit in here. It says limit x tends to 0, tan x minus sin x upon x cube. Obviously, if sin is involved and tan is involved, I would like to resolve this expression by converting tan into sin or writing tan in terms of sin. This gives me limit x tends to 0, sin x upon cos x minus sin x whole upon x cube. This results, if I take out the LCM, this is sin x minus sin x cos x whole upon cos x into x cube. Limit x tends to 0, sin x comes out common, you have 1 minus cos x whole upon cos x into x cube. Sin x is there, 3 x's are there in the denominator, and I have limit x tends to 0. If you can recall that very limit that we have done, limit x tends to 0, sin x by x is 1. That means limit of sine of an argument upon the same argument when that argument is tending to 0 gives you the value 1. Somehow I am going to use that and create the very same situation. This is limit x tends to 0. What I do is, out of 3 x's, I keep 1 x below sin x, 2 x's below 1 minus cos x, and I keep this cos x of the denominator alone. I have just rewritten this expression in this fashion. Now you know limit of the product is product of the individual limits provided each one of them exists. We are going to justify that each one of them is existing, and therefore right now I am writing limit of the product of 3 functions is product of the individual limits of those 3 functions. So this is limit x tends to 0, sin x by x, you know the limit of this function exists as 1, multiplied by limit x tends to 0, 1 minus cos x is 2 sin square x by 2, 1 minus cos x is 2 sin square x by 2, and this is x square, right? Limit x tends to 0, 1 upon cos x. This limit also you know exists as x tends to 0, cos x tends to 1, because you know limit x tends to 0 1 upon cos x is limit x tends to 0 1 upon limit x tends to 0 cos x. Limit of the quotient is quotient of the individual limits provided both of them exist. Limit x tends to 0 of 1 will be 1 only because it is a constant function, and limit x tends to 0 of cos x will be what? 1. We have done that. So, your limit will be 1 upon 1, that is 1. So, this limit is 1, this limit is 1. What is this limit? Let us evaluate. This is 1 multiplied by, how can I manipulate this? See, right now the argument that is sitting is, this is sine square. The argument that is sitting is x by 2, but I do not have the same argument in the denominator. So, what I do, I try to create it. This is 2 sine x by 2 whole square upon x square by 4 multiplied by 4. Why? So that what happens is, I can write x square by 4 as x by 2 whole square. Now, I have the same argument created in the denominator as well. And this, as I was saying, limit x tends to 0 of 1 upon limit x tends to 0 of cos x. And you can see I am able to write limit of the quotient as quotient of the limits because individually both the limits are existing as 1. So, this is 1 multiplied by this is what 1 by 2 comes out. Limit of square of a function is square of limit of that function. So, limit of sin x by 2 upon x by 2 whole square is actually limit of sin x by 2 upon x by 2 as x tends to 0 whole square. See, what I did, two things I did. First of all, I had a constant 1 by 2. Limit of scalar times a function is scalar times limit of that function. So, I pulled out 1 by 2 outside by that property. Then you know limit of square of a function is square of limit of that function. So, limit of square of sin x by 2 upon x by 2 is square of limit of sin x by 2 upon x by 2. Limit x tends to 0 of 1 is 1, limit x tends to 0 of cos x is 1. So, this is what you have. That means eventually I just need to evaluate this. I know sine of an argument upon the same argument when that argument is tending to 0. If x is tending to 0, clearly x by 2 is also tending to 0. This is 1. So, eventually you get 1 into this limit square, 1 square into 1, and this is 1 by 2. So, your answer is 1 by 2. So, it is 1 into 1 by 2 times 1 into 1. Here it was 1 into 1 by 2 times this limit is already 1. So, 1 by 2 into 1 is 1, into 1 is 1 by 2 only. So, that is what is your answer. Clear? Moving to the next question, we have, if y is this, show that dy by dx is equal to y. Now, there are two ways to approach this question. Let me reveal both the ways to you. Y basically is given to me as 1 plus x by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial plus and so on. 1 factorial, 2 factorial, 3 factorial, they are all numbers, constants, natural numbers. So, dy by dx will be d by dx of this entire expression, right. Now, in here I know differentiation of the sum is sum of the individual differentiations. So, this will be d by dx of 1 plus d by dx of x upon 1 factorial plus d by dx of x square upon 2 factorial plus d by dx of x cube upon 3 factorial and so on. D by dx of constant is 0, d by dx of constant times a function is constant times d by dx of that function. Again, constant times d by dx of that function, scalar comes out, again scalar comes out, d by dx of the left out function. This gives you what in the next step? This is 0 plus 1 by 1 factorial into d by dx of x is 1 plus 1 by 2 factorial d by dx of x square is 2x, 1 by 3 factorial d by dx of x cube is 3x square. So, what have you got? 0 plus 1, 1 factorial is 1. So, 1 plus 2 factorial is 2, 2 cancels out, you have x, 3 factorial is 6. So, you get x square by 2, 2 is same as 2 factorial. After this, if you write one more term, suppose I write one more term, x to the power 4 by 4 factorial, just by following the pattern. Here also you get what? 1 by 4 factorial comes out, d by dx of x to the power 4, right? This eventually gives you what? 1 by 4 factorial into 4x cube. But 4 factorial is 24. This is 6. 6 is what? 3 factorial. So you actually have x cube by 6, that is x cube by 3 factorial. What is this? 1 plus x square by 2 factorial plus x cube by 3 factorial and so on. This is nothing but y itself, and therefore dy by dx has come out to be equal to y. Like this you can prove, or you can directly decode that this is the expansion of e to the power x. If this is the expansion of e to the power x you have decoded, directly you can say that y is e to the power x, therefore dy by dx is d by dx of e to the power x. Differentiation of e to the power x is e to the power x, which is same as y, and therefore dy by dx is same as y. Two approaches, you can adopt any depending upon the marks it carries. Differentiate this function with respect to x. So let's write down this function and differentiate it with respect to x. Sec x plus tan x whole upon sec x minus tan x. I am supposed to differentiate this function. The moment quotient is involved, quotient rule pops in mind, but somehow we need to simplify this, then we are going to get back to the quotient rule. I can write this as 1 by cos x, sec x is 1 by cos x, tan x can be written as sin x upon cos x, then again sec x is 1 by cos x, tan x is again sin x by cos x. Cos x comes out as the LCM, what do you get? 1 plus sin x upon 1 minus sin x, because cos x cancels out from the numerator and denominator. Now you apply the quotient rule. This is your first function, this is your second function. D by dx of 1 upon 2 is 2, this is 2 into d by dx of 1 minus 1 into d by dx of 2. So minus 1 into d by dx of 2, 2 is 1 minus sin x, whole upon second function the whole square, that is 1 minus sin x whole square. This is 1 minus sin x. D by dx of 1 plus sin x is d by dx of 1 plus d by dx of sin x. D by dx of 1 is 0 because it is a constant. D by dx of sin x is cos x minus 1 plus sin x into d by dx of 1 minus sin x is d by dx of 1 minus d by dx of sin x. D by dx of 1 is 0, d by dx of sin x is again cos x whole upon 1 minus sin x whole square. So from here you get 0 plus cos x is cos x. So you get 1 into cos x, that is cos x, minus sin x into cos x. Then it is minus cos x and minus sin. So plus cos x, and you have plus cos x sin x or sin x cos x. It's the same thing. They're real numbers. 1 minus sin x whole square minus sin x cos x plus sin x cos x. Cos x plus cos x is 2 cos x upon 1 minus sin x whole square, and that happens to be your respective differentiation of sec x plus tan x upon sec x minus tan x. Suppose fx is given to be this function, and if limit of f of x as x tends to 1 is 1, what are the possible values of a and b for which this is going to hold positively? Okay, This is my function given to me, and the fact that I have to use to compute a and b is this fact. If limit f of x tends to 1 is f of 1 and f at 1 is given to be 4, 4 is a finite real number, that means limit of the function at 1 is a finite real number, that means limit of this function at 1 is existing. So as limit x tends to 1, f of x is 4, which is a finite real number. Limit exists if and only if left hand limit at that point exists, right hand limit at that point exists, and both are equal to the limit. This implies left hand limit of f at 1 is equal to right hand limit of f at 1 is equal to the value of this limit, that is 4, which is given in the question as f of 1. This is if and only if LHL is existing, RHL is existing, both are equal to the same real number, then I say limit exists and is equal to that particular value. Here it is saying limit is already existing, that means obviously LHL and RHL of f is existing at that point and both are equal to the value of the limit. It is given to be equal to f of 1, you have to decode that f at 1 is equal to 4, so limit is actually given to be equal to f of 1, that is 4. Now left hand limit is 4, right hand limit is 4. Left hand limit means limit x tends to 1 from the negative f of x, this is given to be 4, and limit x tends to 1 from the positive f of x, this is also given to be 4. This can be rewritten as what? Limit, replace x by 1 minus h, because 1 is approaching to, x is approaching to 1 from the left, that means x can take values less than 1. So 1 minus h, where h is approaching to 0. This is given to be 4, and here you can say limit h tends to 0 f of 1 plus h, because here x is approaching to 1 from the right, so x is assuming values greater than 1, it is of the form 1 plus h, x is of the form 1 plus h, where h is approaching to 0 as x is coming closer and closer to 1. That is, now h is positive, understand, h is positive, 1 minus h is less than 1, 1 minus h is a quantity less than 1, if 1 minus h is less than 1, then f of 1 minus h is a plus b times 1 minus h, and 1 plus h is greater than 1, h is positive. If 1 plus h is greater than 1, then f of 1 plus h is b minus a times 1 plus h. B minus, this is just this much, b minus a into 1 plus h. It's fine. This is given to be equal to 4. So what do you get? Limit h tends to 0 of a plus b minus bh. This is 4, and limit h tends to 0. This is b minus a minus ah. Now clearly understand, limit of the sum is sum of the individual limits. So limit of h tends to 0, a plus b minus bh is limit h tends to 0 of a, which is a, limit h tends to 0 of b, which is b, and limit h tends to 0 of bh. Limit h tends to 0 of bh, b is a constant, comes out, b times limit h tends to 0 of h, which is 0. So b into 0, which is 0. Limit h tends to 0 of b minus a minus ah is limit h tends to 0 of b, which is b, it is a constant, minus limit h tends to 0 of a, which is a, minus limit h tends to 0 of ah, a is a constant, comes out, so it is equal to a times limit h tends to 0 of h, which is again 0, so a into 0, which is 0. So you have a plus b is 4 and minus a plus b is 4. What do you get from here? This cancels out, you get 2b equals 8, which implies b is 4, b is 4, then a is 0. Right? If b is equal to 4, you get 4 minus 4, that is 0, and a is equal to 0. These are the values of a and b for which this particular limit is going to exist and is going to come out to be equal to f of 1. Prove that this limit has value equal to minus 4. Let's see. Let's try and prove this. The function is given to us and even the value of the limit is given to us. We just need to prove that it is equal to this value. Limit x tends to pi by 4, tan cube x minus tan x. Clearly I can see that tan x is coming out common. So I will take it out common straight away. I am left with tan square x minus 1 whole upon cos of x plus pi by 4. Fine. This is equal to limit x tends to pi by 4, tan x is there, a square minus b square. Tan square x minus 1 can be written as tan x whole square minus 1 whole square. That is tan x minus 1 into tan x plus 1. A plus b into a minus b is a square minus b square cos of x plus pi by 4. Somehow I need to bring cosine in picture because that is what is the simple expression given to me. So how am I going to do that? I will be converting tan in terms of cos. How? Let's see. This is of the form cos of a plus b, which is cos a cos b minus sin a sin b. Somehow I need to bring this entire formula in picture so that I can compactify and write it in the form of cos of a plus b, and then I will be having like expressions. So here what I do, I keep tan x the same. Tan x minus 1 can be written as sin x upon cos x minus 1. And this I am keeping as the same tan x plus 1. Let's just manipulate one expression and see if we can get anything from that. This is what limit x tends to, this is pi by 4, tan x, this is sin x minus cos x whole upon cos x. Whole upon cos x will go in the denominator, and already you have cos of x plus pi by 4. Fine. I know cos a cos b minus sin a sin b is what happens to be cos of a plus b. So I will not be interested in sin x minus cos x, rather I will be interested in cos x minus sin x. So sin x minus cos x is minus of cos x minus sin x. So I will be taking out minus common. Minus common means minus 1 common. Limit of minus 1 times an expression is minus 1 times limit of that expression because constant can be pulled out of limit. So I will be having minus of limit x tends to pi by 4 tan x cos x minus sin x tan x plus 1 whole upon cos x into cos of x plus pi by 4. Now look at the smart manipulation that you need to do right now. This is limit x tends to pi by 4. This is tan x. In order to create the formula of cos of a plus b, I will be multiplying by root 2 and dividing by root 2 cos x. Again multiplying by root 2 and dividing by root 2 with sin x. And this is tan x plus 1 whole upon cos x cos of x plus pi by 4. Fine. Now you can take out this root 2 common throughout. Root 2 common here, that means root 2 common here, because limit of constant times a function is constant times limit of that function. Now you can replace this root 2 by cos of pi by 4 and replace this root 2 by sin of pi by 4. So you have cos a cos b minus sin a sin b, which is of the form cos of a plus b. So this becomes limit x tends to pi by 4 tan x cos of x plus pi by 4 tan x plus 1 whole upon cos x into cos of x plus pi by 4. That is what you needed to do. That's why so much manipulation were being done. Minus root 2 limit x tends to pi by 4, tan x into tan x plus 1 whole upon cos x. So, this is limit x tends to pi by 4 of tan x, then limit x tends to pi by 4 of tan x plus 1. Why? Because limit of the product is product of the individual limits provided they exist, and they will be existing. Then limit of the quotient is quotient of the individual limits. And so, this is what you have. Minus root 2 is sitting over here. This means limit x tends to pi by 4, tan x is what? As x approaches pi by 4, tan x approaches tan pi by 4, which is 1. As x approaches pi by 4, tan x plus 1 approaches where? Tan x approaches to 1, and 1 approaches to 1 only because it is a constant function. So, limit x tends to pi by 4 of tan x plus 1 is limit x tends to pi by 4 of tan x plus limit x tends to pi by 4 of 1, that means 1 plus 1, that is 2. And limit x tends to pi by 4 of cos x, as x approaches pi by 4, cos x approaches cos pi by 4, which is 1 by root 2. So, this is minus root 2 into 2 root 2, which is minus 4, and you have proved that this limit of this expression comes out to be minus 4. Moving to the next question, we have differentiate this following function with the help of first principle, root sin x. Let's start. We know that we just apply the right hand derivative approach in order to compute the derivative. So, f dash x is limit h tends to 0 f of x plus h minus fx whole upon h. Here fx has been taken as root sin x. So, what will be f of x plus h? Root of sine of x plus h, just replace x by x plus h. So, this becomes equal to limit h tends to 0 root over sine of x plus h minus root over sine x whole upon h. So, obvious step is to multiply and divide by the conjugate of the numerator, that is root over sine of x plus h plus root over sine x, multiply by this expression and also divide by this expression, sine of x plus h plus root over sine x. A plus b into a minus b is a square minus b square. Fine, whole upon h into root over sine of x plus h plus root sine x. Now, you can see in the numerator the pattern is sin c minus sin d, which is 2 sin c minus d by 2 cos c plus d by 2. So, let us write it down. This is limit h tends to 0 2 sin c minus d by 2 x plus h minus x, that is h by 2, cos c plus d by 2 x plus h plus x, which is 2x plus h by 2 whole upon h into root over sine x plus h into root sine x. This is plus over here. Now, this 2 can come down and I can write it like this, and therefore, you can see the clear signaling towards the step limit h tends to 0 sine h by 2 upon h by 2. I have clubbed this together because I know where am I heading towards. Limit of the product is product of the individual limits. So, limit of this function multiplied by limit of cos of x plus h by 2 whole upon, this is root over sine of x plus h plus root sine x. Clear? If h is approaching to 0 means h by 2 is approaching to 0. So here you get 1 because limit sign of an argument upon the same argument when that argument tends to 0 is 1 multiplied by limit h tends to 0 of this complete expression, this upon this is limit h tends to 0 of this upon limit h tends to 0 of this. Limit h tends to 0 of numerator, as h tends to 0 h by 2 tends to 0. So x plus h by 2 tends to x, cos of x plus h by 2 tends to cos x. What about denominator? As h tends to 0, see this is a constant, this is not dependent upon h, this is not dependent upon h at all, so this is going to remain the same. Limit h tends to 0 of root sin x is root sin x only, plus limit h tends to 0 of this particular function, as h tends to 0 x plus h approaches x, sin of x plus h approaches sin x, root of sin of x plus h approaches root sin x. And your answer therefore is cos x upon 2 root sin x. And that happens to be your very derivative of this given function by first principle. That's it from my side. Thank you.